a thematic program on network complexity. My colleague Sriram has organized this beautiful series of events for us, which will unfold in the coming couple of weeks to a month. We had a series dedicated, a course dedicated to equilibrium statistical mechanics about 3 weeks ago, with the second guiding us through a beautiful exposition of the subject, leading up to a network models, which I'm sure you'll find very interesting. This week we have with us Sriram Ramaswamy from the Indian Institute of Science in Bangalore. I will leave the introduction, the scientific introduction, to Sarah. Of course, he will be talking about the hydrodynamic models for active matter, and I will just give you an anecdote. So in the mid to late 90s, I was visiting Bangalore, visiting the Institute, where we have friends, and we were discussing the physics of beer models, and you should try to of course, on the benefits of active matter, looking at the discrete values. The Institute repeatedly, and it's like a second home for me, second scientific home for me. Say you have to meet Sriram, definitely a legendary pedagogue and a creative researcher within the Indian community, and certainly worldwide with his contribution to complex sets of physics. And I look forward to meeting him on the next visit to Bangalore. Okay, and I will let Sarah introduce him on the scientific end of his contribution. Thank you, Sriram. Thank you very much.
Thank you, Jihad. And after this introduction of Sriram, I'm very delighted to have him here with us, go online, and I'll do the scientific introduction as he had wished us to do. So he was born in Lucknow in 1957 and started his education at the Modern School in New Delhi, where he graduated in 1973. Then he got his bachelor from the University of Maryland in 1977, and then the PhD from the University of Chicago in 1983. Then he started his postdoc at the University of Pennsylvania from 1983 to 1986, and then he's been on the faculty of the Department of Physics in the Indian Institute of Science from 1986 till present. He was a professor since 2002, and he's been on leave from 2012 to 2016 as the center director of the TIFR Center for Interdisciplinary Sciences at Hyderabad. His current research interests are non-equilibrium soft matter and biological physics, and is widely recognized for his research on active matter, a field he helped created. And he's been the elected fellow of the Royal Society of London in 2016, and Infosys Prize for the Physical Sciences in 2011, and Shanti Swari Prize for the Physical Science in 2000. So we're very happy to have you with us, Sriram, as he would like you guys to call him. And please, he's going to start his slides, and it's a lecture, so please feel free to unmute yourself and ask questions when you need to. And we'll start, the session is recorded, so it's going to be available on YouTube, on Cam's channel after the session is done. And thank you.
Okay, I can start?
Yes, sure.
Okay,
but you have to screen share as well if you want to share the slides.
Yeah. Thank you, Sarah, and everyone for this very kind invitation and very kind introduction. So let me start my slideshow. It's a great pleasure to be with you virtually. I'm really sorry not to be there in person. I've heard great things about Beirut since I was a kid, actually, because my father has traveled there on work when I was a school kid. And so I've heard great things about it. I hope one day to actually visit in person. Anyway, the title I put up here is just the title that I was that was on the poster. I guess it's probably the way I'll really organize the talk is that I'll talk about mainly about ordered active matter systems, and I'll start from simple systems and go to slightly more complicated ones. That's my main research support. So let me begin. As I understand it, I'm giving 3 lectures. So in my first lecture, I'll give you sort of general fundamentals on the subject of the kind of statistical dynamics that I'm going to talk about. And I'll actually connect active dynamics I'll sort of draw a thread from equilibrium Ramaswamy equations to the dynamics of active systems. Then I'll use that general framework to formulate broken symmetry hydrodynamics of active systems and talk about it in one specific context, namely flocking models, actually without any mention of fluid. I'll then, my second lecture, if all goes as planned and as I've organized, my second lecture will be on flocks and fluid, and I'll talk about 2 rather different regimes. One is low Reynolds number, and the other is sort of intermediate Reynolds number, and a rather novel type of turbulence related to something that people have been studying in the field, but somewhat newer. And in the third talk, I'll talk about translationally ordered systems, proceeding in increasing order of complexity. And I'll talk about active systems with positional order, like active crystalline materials and active liquid crystalline materials with positional order in various directions. This last, I guess, the lectures will also in some sense be in increasing order of technicality, apart from increasing order of complexity in the structure. So let me start. I'm really happy to have the students interrupt with questions in the middle of the talk. As I see it, there's about a dozen students in the audience or so, and feel free to just unmute and ask a question, because I don't have a very strong agenda to finish a certain amount of material. So let me begin. So condensed matter physics is about the collective behavior of large numbers of interacting particles. Those interacting particles, could be molecules in a gas or fluid or solid. They could be spins in a magnet. They could be elongated molecules that form a liquid crystal. But in general, we'll call those constituent objects of our system particles. Now, normally, when you study statistical mechanics and thermodynamics, you consider systems. Either you consider isolated systems whose total energy is constant, or you consider a big system which is isolated and you take a subsystem and you speak of that subsystem exchanging energy with the bath. And this exchange of energy is back and forth. So what you have is either a system with an actual exactly fixed energy budget, or you have a system with a fixed average energy, but it exchanges energy with a bath, and the subsystem and the bath together are isolated. So in both of these, roughly in equilibrium physics of the sort that you are accustomed to learning about in your courses, you have systems that are effectively at a constant energy budget. But if you take any of you or me or any living organism, we don't work at a constant energy budget. We work at we work at a steady energy throughput. We constantly take in nutrition or some kind of source of energy, and we convert part of that into some kind of systematic movement, and we throw out some waste. So active particles like us or like any of our cells are alive in many ways, but from the point of view of the kind of mechanics I'm going to talk about, they are powered. They're not like, it's not like our body is like a wire and there are batteries connected at the ends. Each component of our body, each cell is powered. It has an assured supply of free energy, which it converts into systematic movement, right? That means each constituent carries a kind of arrow of time, a dissipative arrow of time. Collections of this kind of particle, collections of active particles, are called active matter. Okay, and that's the kind of system we're going to be interested in. So matter under conditions of sustained energy throughput, not sustained energy budget. Okay, and these systems, there's a rich variety of these systems. In all of these systems, as I said, each constituent is driven, it carries a dissipative arrow of time. So that means the condition of detailed balance, which you may have read about in your statistical mechanics or chemistry courses, is deliberately broken by the permanent presence of a source of power, which is carried one way from power to waste by converting into movement. Okay. And this breaking of detailed balance, this permanent state of disequilibrium at the level of particles, means the particles do many things that equilibrium matter doesn't do. For instance, here is a collection of little chemically propelled droplets. They're droplets which contain something that wants to dissolve in the surrounding fluid. And they contain so much of it that this process of dissolution goes on taking place. And so you have some material going from a low entropy state to a high entropy state in a sustained way and running around as a result. So you can think of this as scalar active matter because the particles themselves are more or less little round, tiny little droplets. You can imagine vectorial active matter. Let us say, here is an exotic artificial example. What you are seeing in this picture is the top view of a system, okay? You're looking at it from above, and that system is being vibrated. It's not being vibrated horizontally, it's being vibrated vertically, that is to say, it's vibrated towards you and away from you as you view it, okay? So if you look at my hands, it's being shaken up and down like this, and the particle is sitting on it like this. And what's happening is because the particle has a funny shape, the particle is tossed up and comes down, and it typically comes down one end first rather than the other. And because of static friction, when it comes down at that end, it doesn't just slip back. It ends up being impelled forward along this length. So what you're seeing here is a very elementary energy conversion device. You shake the system up and down, particle sitting on it takes that shaking energy, which is subject to move vertically, and converts into motion horizontally in the plane. It walks, okay? So in this system, the vibration, the vertical vibration of the plate is like the energy source. The angle, the tilt coordinate of the particle with respect to the surface is like the internal coordinate of the motor. That energy source together with the tilt coordinate, which is coupled to the base through static friction, leads to a seemingly self-propelled object. Pictorially, it's a very trivial example, but it works. You can imagine more subtle kinds of breaking of detailed balance, breaking of equilibrium. Let me show you one of these. Here is a collection of particles on that same vibrating surface. But these particles, structurally, although not all of them are perfect, they are roughly the same at the two ends. It's true that they're not perfectly designed. This end and this end are more or less the same. As a result, when the surface is shaken up and down, they don't move systematically in one direction. They move roughly randomly back and forth along their length. The important point here is they move more along their length than transverse to their length. That means they have more kinetic energy in this direction than in the perpendicular direction. So if you look at, I assume you can see my pointer here. I guess it's not showing too clearly, unfortunately. No, yeah. The particles have more kinetic energy in the longitudinal direction than in the transverse direction. Now, you've studied you've studied kinetic theory of gases, and you know that any classical gas has every bit as much kinetic energy in every one of its degrees of freedom. Translation along X, translation along Y, translation along Z, rotation along any axis. So these particles are out of equilibrium in that rather delicate way, in that they have different amounts of kinetic energy in their longitudinal and transverse motion. These two are active particles. On average, they don't go anywhere, but collectively they can do some very interesting things. Okay. These collections of particles of this sort are described by a scalar quantity like their number density. Collections of particles of this sort would be described by a vector field describing their average direction in which they're pointing. Particles of this sort would not be described by a vector, but by a tensor order parameter. I may or may not have time to talk about that in these lectures. And you can have a host of other systems. Notice all three examples I've showed you are not of real living matter. They are all artificial. This one is an elementary chemical energy converting device, and these two are elementary mechanical energy converting devices. Okay? You can even have active states in two-dimensional electron gases pumped by microwave energy in the third direction. Or you can make active matter by extracting filaments from a cell, extracting the necessary chemical fuel, namely ATP, and you can create spectacular structures like this periodic undulated state made of actin fibers with myosin motors and ATP. And you can have other kinds of symmetries in these active systems. You can have objects which are chiral, which turn as they move, and so forth. So there's a huge host of different kinds of systems that you can have. Apart from this, of course, I guess I don't have curiously enough, I don't have an example of a living system in this particular set of slides. But obviously, living matter is the other kind of thing we would like to describe. Even if you limit yourself only to uniaxial order, okay, or using particles with a single axis and order with a single axis, you can imagine order described by the alignment of a bunch of arrows that will have a vector order parameter. Or you can imagine that the particles have an arrow, but their alignment is randomly forward and backward, keeping the axis of the arrow parallel, but the direction of the arrow random, in which case you get what is called apolar or nematic order. You can have that even if the particles are polar themselves, or you can have particles which are themselves apolar, lining up only their axes. You can also have particles which possess a head-tail symmetry when it comes to their dynamics, but structurally might show no sign of a difference between front and back. So there are many such broken symmetries that are possible. You can also imagine, as in any condensed matter system, you can also imagine systems in which translational order is broken. For example, within elementary flocking models, the onset of the flock state actually takes the form of a spatially periodic modulation of the density together with motion in some direction. So this system breaks translational symmetry. You can take standard examples of liquid crystalline order, such as this lamellar or smectic phase, which is one-dimensional translational order in 3 dimensions, or this hexagonal columnar phase, where you have what you can think of as a collection of one-dimensional liquid columns packed in such a way that any horizontal slice through this shows 2-dimensional crystalline order, but the columns are free to slide relative to each other without doing any reversible work. You can also have, in that same vibrated system that I talked about, you can imagine a collection of beads forming a crystalline lattice. You can imagine energizing those beads with little motile particles running through them. You can have systems in which the translational order is due to the periodic rotation of an orientation field with respect to a pitch axis. You can even have systems which break translation invariance, but in a random way. You can have an amorphous packing of beads, and you can energize those either by vibration or by motile particles running through them. Like this, you can imagine our old friend, this self-propelled particle, moving through a medium which is so densely packed that it's not a fluid, but in which the particles are random in size, so it doesn't crystallize either. So there's this rich collection of possibilities. Basically, you can take all kinds of phases familiar to equilibrium physics and look at their analogs in the case of active systems. You can also have systems which display types of order which an equilibrium system never could display, such as time periodic dynamics. perpetually oscillating dynamics, of which I'm afraid I don't have any pictures. Okay. All right. So those are the types of order. What I want to discuss today is if I had any of these systems. Imagine, for example, that I have just one of these particles. Okay. Imagine I have a particle like this. Okay. Imagine I have a particle with a head and a tail. And imagine that imagine that the two ends have a response to a force which depends on whether this object is stretched or compressed. But imagine that the noise on the two heads doesn't care about whether it's stretched or compressed. Okay, let me repeat that idea. I have an object with a head and a tail. Both the head and the tail move with a speed proportional to the force with which they're being pulled or pushed. But imagine that the proportionality constant between the force and the velocity depends on the state of stretch of the object. But imagine you agitate the two heads randomly with a random force that doesn't care about whether the object is stretched or compressed. It turns out that is enough to break the conditions of thermal equilibrium, to break detailed balance in a subtle way. And that leads to a net propulsive force on this object subset. So this is a mathematical model of a self-propelled timer. What's happening basically is that the net result of this funny breaking of equilibrium is that the object acquires a velocity proportional to its stretch. Okay. Now, supposing to begin with, I just wanted to write down a theory of a system with a few degrees of freedom. Basically, what I have is, and I want to describe both the energy consumption and the motion of the system. Okay, let's build a framework to describe this. I have a question before I go further. Is the class familiar with Ramaswamy equations? Are the members of the audience familiar with Ramaswamy equations?
Yes,
Yes.
I am.
All right, great. Okay. So I'll assume that I can go ahead with that framework, right?
But I think not the undergrads. So the
Not-
class is kind of split into people who know it and people who don't.
So maybe I can actually write down a few lines on a screen. I'll open as I said, I don't have a big agenda, so I can actually, I'll use yeah. So you won't be able to see my face right now, but that's okay. You can see what I'm writing?
No.
Yeah,
Yes, now,
yes.
yeah.
All right, okay. So maybe I can just spend a minute on this topic. Let's say I've got a somewhat medium, a few micron size particle. Size in the middle of a medium. Sorry. Excuse me. In a medium, in a fluid, in a gas or a fluid. Okay. So I've got lots of little gas molecules. So and these fluid molecules bounce off this particle, and I want to know how to describe, and let's say this particle has a mass m, and the fluid exerts a damping gamma. So then I'll say that m times dv over dt of the particle plus gamma, so equals all the forces acting on the particle. Maybe there's an external force field, such as gravity acting on it. And there's a damping, and we'll make a sensible rule for the damping. This is what Mr. Langevin did. He said that the particle is damped by a force proportional to its velocity. But he said something else. He said, it's also moving around at random, as people could see through a microscope, with a little random force. And what he said, and what Einstein said in some sense, was that the damping and the random kick are actually coming from the same origin. If the particle is left to itself, it's kicked around at random. If the particle happens to be moving in a particular direction, then it gets kicked more in the front than in the back, and so you get a random force. It turns out that if we model this random force in the following way, and let me write, just for simplicity, let me write a one-dimensional picture of this. Let me forget about all the vector signs. Okay. If I assume the force is completely random in time, then its average is 0. And from one instant of time to another, it's uncorrelated. Some constant times a delta function of t minus t prime. Then it turns out that if you insist that the particle's velocity is in equipartition at that temperature, that means you insist that half mv squared, this is one dimension, remember, is equal to half kBt, then all you need to do is for this constant and the damping to be related in this particular way. So you can now generalize this to a system with many components, but all I really want you to get is that if you want to describe a particle which is being kicked around at random by the molecules of a surrounding medium at a certain temperature, and you want that particle and all the other particles to be happily in thermal equilibrium with each other, then all you need to do is to write down an equation of motion in which, in addition to any systematic force you're applying on the particle and a damping, you introduce a random force and you insist that that random force is zero mean, is Gaussian, is a Gaussian random variable, and it's completely random in time. That is, it's uncorrelated from one time instant to the next. And the strength, the variance, if you like, of the noise is precisely twice the temperature times the damping. If you do this, then you will describe a particle which, even though it's bigger than the other molecules in the medium, is completely in thermal equilibrium with them. This particle's kinetic energy, as well as all the kinetic energy of all the molecules in the gas, will all be equal to, on average, equal to half kBt per degree of freedom. Okay? So this is Langevin's equation. We're going to use this as a starting point. And now I should somehow come back to the... hang on a second. Why is my camera not working? Just a moment. I'm having some technological trouble here. Oh. Can you hear me?
Yes, we do.
But you can't see me, right?
We can't see you, neither the slides. So
Neither me nor the slides. So my
Yeah.
interrupting the talk to write on the screen proved to be a disaster. I see. Okay. Let's see what we can do about that. Give me a minute.
sure.
What can you see on the screen?
Nothing at the moment.
Nothing, is it? Okay. Now?
Okay, yes, you're back. But not your camera, but just the slides.
Right. Okay. That may just be some other.
Yes, I think it's
yeah, now I
back.
have to put the right camera. So.
Yeah.
Yeah, there's one more piece of technology I have to fix here. Sorry about this. Hmm. It basically doesn't allow me to share. I think I'll do the obvious thing, which is I just disconnect and reconnect. Give me a minute, okay?
Sure.
That always works. That day. Didn't figure out how to get out. Right. Yeah. Okay, so where were we? So what I'm going to do is I'm going to extend that Ramaswamy equation framework to describe systems that are active. And I'll tell you exactly what I mean. The basic idea, when you have anything that's self-propelled, anything that's converting energy into motion, what's actually happening? If you take crudely, any living organism is consuming fuel, which I will describe as moving in that direction. Let us say X. Think of X here as the number of fuel molecules consumed. So as the chemical reaction that powers us goes on, as conversion of ATP to ADP and so forth, and extraction energy goes, we're moving chemically in this direction. That's a coordinate of a kind, a coordinate describing the progress of a chemical reaction. And the coupling between chemistry and mechanics means that as a result, that little device that's converting chemical energy also moves in a spatial direction. Pictorially, you can imagine it as, imagine if you had a sort of corrugated landscape. Imagine you had a sheet with grooves and you had a particle that you place in the groove and you are pushing that particle gently in that direction. And what you find is the particle, because it's in a groove, when it tries to move that way, it also ends up moving that way because it ends up moving diagonally. So it's as though you have a mobility matrix in this two-dimensional space, and the particle has a velocity vector in this two-dimensional space, which even if the force is in that direction, doesn't move in that direction alone, it moves this way, which means while it moves that way, it also moves this way. Okay, so force is that way, mobility matrix is non-diagonal, therefore motion rather than being parallel to the force is in an abstract sense at an angle to the force. And therefore, you end up moving in the spatial direction as well. Now, this is not a theory of active matter. This is simply a compact description of what it means to carry out a sustained chemical reaction and as a result move spatially, or what it means to have to drive one coordinate and have the other coordinate also execute translation. Okay, so this is the picture. Now, how do we build a mathematical description corresponding to this? Okay, one of the major aims of our description will be to make sense of the following idea that when people write down equations of motion for a system at equilibrium, they have a certain way of writing those equations and they get a certain structure. Then someone says, you know, my equation, my system is out of equilibrium, so I'll write down new terms that weren't permitted in the equilibrium dynamics. I'll try to make that notion of writing down quote unquote new terms precise. Okay, and here's how I'll do it. Let's consider a completely general system consisting of two coordinates q and x and two momenta p and pi. Okay, think of p as conjugate to q, pi as conjugate to x, but don't take that conjugate notion too seriously. Imagine you have a system, you've got a complicated system, and you've sort of simplified your description to where you have one coordinate, always keeping in mind this picture that we're trying to describe this idea, okay? Pushing in one chemical direction, achieving movement also in a physical direction. So imagine you have two coordinates q and x, two momenta p and pi, and ultimately x will represent the chemical coordinate and pi will represent some kind of velocity of that chemical reaction. Okay? And imagine the system as a whole is governed by Hamiltonian H. And imagine right now, let's first do the equilibrium dynamics. Imagine that the system as a whole is at thermal equilibrium. We're going to relax that presently, but right now, imagine the system as a whole is at thermal equilibrium. And I think of q and x as coordinate-like and p and pi as momentum-like. That is to say, q and x don't change sign under time reversal. P and pi do change sign under time reversal. Okay, and if I was just writing down Hamilton's equations for this system, I'd say q dot is del h over del p, x dot is del h over del pi, p dot is minus del h over del q, and pi dot is minus del h over del x. That's all I will do. But now, supposing I introduce damping to this system, damping is proportional to velocity. Velocity is the derivative of a Hamiltonian with respect to the momentum, right? If your kinetic energy is p squared over 2m, if you differentiate that with respect to p, you get p over m, which is a velocity. So my modified description of this system, once I include damping, is not only the Hamiltonian dynamics, which involves these terms and these terms, but a damping which will in general involve terms linear in the velocity in the equations for the rates of change of the momentum. Okay, I can see I'm going rather leisurely, but that's okay. I'd rather I conveyed a little bit adequately. So now let's introduce damping. First of all, if p and pi weren't coupled to each other at all, you just get one damping coefficient here, right? A kinetic coefficient gamma 1 times del h over del p. That's just damping equal to some friction constant times the velocity. The same thing pi would have gamma 2, let's call it, times del h over del pi. But now I want to couple these mysterious internal variables x and pi to the manifest variables q and p, which are going to be my physical coordinates. I will do it by saying that in some way, when one of the variables, when the x variable has a velocity del h over del pi, its movement somehow drags the other variable as well. Okay, and when the Q variable has a velocity del H over del P, it somehow drags the pi variable, the X variable as well in this way. Okay, so I'm introducing an off-diagonal damping constant. Okay, it's not physically very hard to see why that might happen. If you have a wind blowing and you have, let us say you have a little pinwheel, you blow a wind at it, the drag of that wind acts asymmetrically on the object in such a way as to give it a velocity. So the wind has a velocity and the wind transfers its momentum to the other object and makes it turn, right? So the wind blows at a sail and makes it turn. So you can think of those as a drag on one velocity, one object having a velocity which through drag couples to another object. That's the picture I have here. Now, I have to do more than that because I want to talk about a system coupled to a thermal bath. So the moment I introduce damping, I also have to introduce noise. And this is why I introduced the Ramaswamy equation for one particle. And I said, anytime you have a noise, that noise, those are zero mean Gaussian variables, and the correlation functions of that noise are proportional to the corresponding damping coefficients. Okay. Here, what I've done is I've introduced off-diagonal damping coefficients. And therefore, not only is the eta correlator proportional to gamma 1, 1, and the C correlator proportional to gamma 2, 2, the eta C correlator is proportional to gamma 1, 2. Okay, there's a deep principle of physics that says that gamma 1, 2 and gamma 2, 1 have to be equal. The important additional input we're going to give ourselves here is that these off-diagonal damping coefficients, as is perfectly permissible, are going to depend on the physical coordinate of interest. This seems like a very complicated way of constructing active dynamics, but I'll show you that what you get in the end is intuitively reasonable. Okay? So what am I going to do? I'm going to do a couple of things. I want to get an effective dynamics of Q in which I don't look at P, at X at all. Okay? I'm going to first take this velocity of the X coordinate and eliminate it from these equations in favor of the force on the X coordinate. So I'm going to do two things. One is I'm going to assume that the X coordinate involves particles of mass that's so little that I'll forget their inertia altogether. So I leave this term out. I will then say that this velocity del H over del pi is determined by the force on this coordinate and on this term. So I'll take this equation and use it to replace del H over del pi. Okay, let me go back. I'll take this equation, solve it for del H over del pi in terms of del H over del X and del H over del P. Okay, thereby getting, so I'll eliminate this guy in favor of del H over del X and del H over del P. And so my momentum equation for the variable I'm actually interested in, Q and P, the momentum equation not only has its original damping, it will get a piece from here proportional to del H over del P, and it will somehow get this force coming in a funny way. The end result is that my P equation will have a new damping, which is the old damping plus some corrections, and it will have a new force, which is this combination. Okay, so now I've actually done nothing. So far, I can still regard my system as being a set of coordinates Q, X, and P at thermal equilibrium. And I have an X equation of motion, which looks like this. So the chemical reaction proceeds in this manner. The chemical variable, the force on the chemical variable, enters the momentum equation, and I have this pair of equations. Okay, this is still thermal equilibrium. This process of transforming variables has changed the random force, has changed the damping, has turned the damping into this new object, has changed the random force into this combination of the noise that was originally in this equation and this chemical noise. But the new noise and the new damping again satisfy the same condition that the autocorrelation of the new noise is the same temperature times the new damping. So right now we're still at thermal equilibrium. Now what I'll do is I'll say the magic word, which is that I'm not at equilibrium. If I was at equilibrium, the average force on every coordinate is 0. I will insist I'm not at equilibrium. I'll hold my chemical coordinate, the force on my chemical coordinate, del H over del X. I'll hold it at a fixed value, which I'll call delta mu. If I think of the force on the chemical coordinate as the force that is driving the chemical equation, that means that force is the chemical potential difference between the reactants and the products. So if it is ATP and the reaction product is ADP plus inorganic phosphate, for those of you who are totally steeped in physics and aren't exposed to biology, the chemical fuel in our system is a thing called adenosine triphosphate. Cells in our body, molecular motors in our body, hydrolyze that ATP and turn it into ADP and inorganic phosphate and gets an energy out of it. And that's one of the central reactions in our body. Okay, so this delta mu would be the chemical potential difference between reactants and products. So if I do that, then this del H over del X, this del H over del X becomes a constant, which I'll call delta mu. And now my P equation, in addition to an ordinary damping and a force, systematic force coming from its Hamiltonian, all of a sudden has acquired a new Q-dependent force. This is the general reason why, when you have a system that's held far from equilibrium by driving some hidden chemical process, the equation of motion for that system acquires new terms, not obviously connected to the Hamiltonian system. Okay? Excuse me, mosquitoes in my office. Okay, all right. So this is how you build active dynamics from equilibrium dynamics. You take a coupled dynamics of two variables, one of which you think of as chemistry, and you introduce a chemomechanical coupling in the form of an off-diagonal damping, and you allow that damping to depend on the physical coordinates. And then suddenly and miraculously, you have a very general family of equations of motion. You understand their connection to a more microscopic description in terms of coupling of the mechanics to the chemistry. But you can now say, look, I don't care about the chemical dynamics anymore. I'm only interested in Q and P. I know that my equation, as long as the chemical force is held constant, has new terms in it, whose form I would never have guessed at a priori. Those terms can be any form that's allowed by the symmetries of the system, the spatial symmetries. I have broken time reversal invariance by insisting that this chemical reaction proceed on average in one direction. What that means in practice is I've got my active system. It uses fuel and turns it into motion. I keep that fuel tank full. As and when it uses fuel, I keep topping up the tank. So I am interested in the steady states that result in systems where I drive some process by fuel by going on topping up the fuel, and I ask what the emergent dynamics is of the physical degrees of freedom. Okay? So the end result, therefore, is this so-called new terms. All those quote-unquote new terms arise because the off-diagonal kinetic coefficient is allowed to have very general dependencies on this other physical spatial coordinates. Now, I agree that this is a rather heavy load with which to begin a lecture. I lulled you into a false sense of security by showing you movies of interesting moving objects, but then I launched full tilt into fairly complicated, fairly technical dynamics. So maybe this is a good moment to pause after I just say one thing. You can also take a reduced description of the dynamics by saying that I'm working in a regime where damping by viscosity or friction dominates over inertia. So I'll throw away the inertia in this equation. I'll therefore replace the velocity variable here, del H over del P, the momentum, by an expression in terms of the coordinates and get an effective first order, no inertia dynamics of my variable Q. Q dot is mobility times del H over del Q, plus extra terms coming from the fact that it's active, plus a noise. Okay? Let me pause and see if I've completely snowed people, and feel free to go back as far as you like into the lecture and ask questions. Okay. Any questions? Or Sarah, if you like to. Yeah.
I have a question.
Yeah.
Early on in the lecture, when we were talking about the symmetries, the polar and nematic
Yeah.
symmetries, do normally systems tend to have only one? For example, it's either ordered nematic or polar, or can it exhibit different types of?
Actually, you can have, it's a good question, very, very important question. You can have systems with fairly complicated types of order. You can imagine, I mean, even if you just look at the world of liquid crystals, you will see that there's a very intricate set of types of order that can happen. Even nematic order, you can imagine two kinds. Let me again use my hands and use some props. You can imagine an object like this, which is just a rod, and you can imagine the rods, the axes of a whole bunch of rods all lined up. You can imagine instead that the object that's aligning looks like this. You know, many molecules not only have a long axis, they sometimes also have a flat face perpendicular along, along that direction. So you can imagine in principle a collection of objects like this lining up not only their long axes, but also their faces. That would be biaxial order. If a system has both vectorial, now take this fountain pen, this pen, for example. It's got this end different from this end, and it's got an axis. If the vectors all line up, then the fact that the axes have also lined up becomes subsidiary. That is to say, if you've got vectorial order, then nematic order turns out to be slave to the vectorial order. That is, the average amount of nematic order will be essentially proportional to a quantity that you can construct from the vectorial order. So some types of order become, that is, in a long wavelength, long time description, some types of order become subsidiary to other kinds of order. Similarly, just going back to ordinary equilibrium physics of crystals, you know that when something crystallizes, it breaks not only translation invariance, but rotational invariance as well, right? However, when you look at the long-time dynamics of a crystal, you only look at the lattice vibrations, you only look at the phonons, right? You don't look at any orientational modes as a separate dynamical variable. The reason is that the orientation, if you take the crystalline lattice and try to change local orientations, keeping the lattice positions fixed, the orientations relax quickly to directions determined by the average lattice directions. Okay, so certain types of order are subsidiary, and therefore, even in some systems, when those types of order coexist, only one of them matters. But you could imagine, weird systems like I was showing you. Imagine you had objects that were rod-like along one axis and had some side group that ordered like this. So then what you'll have is something which has two axes. In this direction, it's uniaxial and without a polarity, and in this direction, it's uniaxial and maybe it has a polarity. So lots of possibilities do exist of that sort. I hope that answered your question.
Yeah, it does. Initially, when I asked it, I was thinking maybe if it depends on the number of agents in the system. It could, for example, if they're crowded, we could move to some apolar model.
Okay. That's
only a few, then.
Certainly, in general, the state of order will depend on the density, on the how packed the system is. If the system is very loosely packed, it will most likely be isotropic. As you pack more densely, you will find that purely out of a kind of, for statistical reasons almost, things end up condensing into aligned states. I mean, for example, again, if you forget active matter physics, if you think of ordinary equilibrium physics, supposing you imagine you have a collection of particles with no potential energy of interaction, only a hard particle constraint. Suppose you have a bunch of hard spheres, and you ask, what is the statistically most likely state of the system at low densities, and what is statistically the most likely state of the system at high densities? At low densities, it turns out to be a fluid. At high densities, the same system maximizes its entropy by ordering. So entropy is not a measure of disorder. Entropy is a measure of how many states the system has. And when you start pack things, at high packing, the system acquires more available room for local translational motion if it arranges its particles into a lattice. Similarly, if you take long ellipsoids and try to pack them, at low densities, they'll point, the most likely and therefore the thermodynamically favored state will be isotropic. As you increase packing fraction, pure hard spheres, no attractive forces, pure hard ellipsoids, will spontaneously align because that is their state of maximum entropy, as Onzaga proved in the 1950s. So packing is very important. Density, crowding is very important.
Thank you.
Okay. So as far as the Langevin equation stuff goes, I'll go ahead assuming that you've accepted this general idea that if you have, yeah.
Okay, so I can see how the formalism is presented at the end with the.
Sorry, I can't hear you.
Can you hear me now?
It's very soft, actually. When Sarah was talking, I was able to hear. When you're talking, I'm not able to. I'm not sure. Maybe you're using a different mic.
Can I press anything? Or no?
Still rather faint. I don't know.
Maybe it's a communication issue.
I'm not sure that this microphone picking.
Yeah, sound.
How about now?
Yeah.
Okay, so I can see how the formalism presented towards the end captures aspects of motility in the context of biological systems. But I couldn't help wondering when you arrive there.
Again, it's getting very soft. Sorry.
Hello?
Do you want to type your question into the chat? I can look at it.
Wait. Can you hear me now? Hello?
I can't hear you. So if maybe you want to type. Right.
We'll use the mic that you were able to hear.
Yeah.
Okay. So I was saying that I can see how the formalism presented towards the end captures motility in a biological setting with.
Right.
But now I couldn't help but wonder when you allow for internal degrees of freedom, whether in the context of an unholonomic situation where an internal degree of freedom is undergoing a cyclical variation, you could actually find an external degree of freedom acquiring phase in the context of these cycles. And if you didn't.
Yeah, it's true that this description, in some sense, averages over those internal cycles. Because after all, so what it's really doing is it's hiding the mechanochemical coupling that is really responsible.
Right, but the question ultimately, in the context of an unholonomic phase, do you actually need friction? You don't need drag in the system to bring about a change in the effective variable, in the Q variable, which you're interested in. Once you allow for internal degrees of freedom, you can envisage situations where purely Hamiltonian settings with cyclical variations can bring about an evolution in the variable of interest. Is that of interest to you guys?
Yeah, so I mean, okay, let me just try to share the screen and see if the way in which I'm writing the equations. So supposing you look at just this last equation, what I'm saying is that the way I've written it here, the general, let's ignore all the elaborate formalism that went before. If you just look at this way, my claim is that a fairly generic way of describing these kinds of active motions is that there is a force on some chemical coordinate, and at least at this level of description, the motility is indeed achieved by saying that I have a driving force and I divide it by a friction or multiply it by mobility. If I didn't have a drag, if a driving force had a purely reversible effect, it would accelerate the system and you need a damping to slow it down. So if you look at this picture, if you like, if you look at, okay, let's start. I mean, maybe I'm not understanding the drift of your question, but supposing you have a system described by coordinate and momentum, and I have a chemical driving force here, then in this form of the dynamics, the effect of the internal driving is actually given by a systematic force which has no friction in it because it's a ratio of 2 damping coefficients and is therefore actually a reversible kinetic coefficient. The reason this coordinate ultimately acquires only a finite velocity is that it is damped. So I don't know if I answer your question at all, because again, the sound started trailing off.
Shift my question to an email and we can try to exchange separately. Thank you very much,
Okay,
Sriram.
all right. Sorry, I'm not giving you a complete answer. Okay, so what we're going to do is we're going to use this approach. So all right, so let's see. By the way, how long am I supposed to talk?
Tentatively an hour and a half.
I have an hour and a half, right? Okay, fine. Yeah. Okay, so I have enough time to tell you a couple of stories today. Okay, so let me give you one toy example. Remember that funny self-propelled dimer I showed you? One way of viewing that dimer is actually to say that, let's say it has a relative coordinate capital Q, a center of mass, is that how? Yeah, a center of mass Q coordinate small q, a damping that depends on the stretch capital Q, an off-diagonal coupling between the physical and chemical coordinates, and you can actually write down equations of motion for this object, which will precisely give you a propulsion, of this center of mass coordinate by an amount proportional to the stretch of the relative coordinate. This again is not a theory of the motility of this object, it's a redescription of that funny motility that I showed you. And then depending on the potential that you subject this internal relative coordinate to, this dimer can actually be something that on average wants to relax to 0 and propels whenever it's somewhat extended. Or if you have a potential for that internal coordinate that looks like this, it can have a preferred length and therefore have a preferred speed. So you can describe a sort of a host of fairly simple systems using this language of active dynamics. What I want to do in today's lecture probably is only, let me just check, stop sharing for a second. Yeah. Yeah. Let me do the following, okay? Let me tell you how you can start from what looks like a model of a bunch of little rotors that want to line up, and how I can turn that into a model for a bunch of objects that actually want to flock. Okay, here is how I go about it. Supposing you have, you should think of this P as a 2-dimensional vector field. Okay, imagine I have a 2-dimensional system, and at each point, I should have a cartoon somewhere. Yeah, so imagine I have a 2-dimensional system, and at each point of that 2-dimensional system, I have a little rotor. Unfortunately, I haven't drawn arrows on these heads, but imagine each of these is a little arrow. Okay, and imagine they have some rule that makes them want to line up with each other. Okay, I don't think I've written down the rule here, but it doesn't really matter. And imagine I have some function f of the field P, which is so constructed that it wants to create a state where P is non-zero. That will come the next slide, probably. No, unfortunately not. Okay. Yeah, it does, yeah. So imagine f is this functionality. Okay, there's a p squared term, a p fourth term, and a term that says that that penalizes spatial variation in p as well. These two terms together, if a is less than 0, will favor a local non-zero value of p, right? If this is minus something times p squared plus something times p fourth, then this part of the energy favors the formation of a local moment, a local non-zero, a local p of non-zero magnitude equal to the square root of mod A over B. And this term favors uniformity in P everywhere. So you can, in the same spirit as the Langevin equations I told you for one coordinate, you can write down a Langevin equation for the field P, which says that if I ignore inertia, then the rate of change of orientation is a mobility times the force that arises when P isn't at equilibrium, when P isn't sitting at the minimum of this F, and a random force whose strength is proportional to this kinetic coefficient and temperature. This would be the description of the dynamics at thermal equilibrium of a bunch of these little vectors. What would happen in this model, depending on how many space dimensions you're sitting in, is that if you lower the temperature, okay, physically, let's assume that the coefficient A becomes negative at sufficiently low temperatures. Then what will happen in this system is that at high temperatures, the P's will be pointing every which way, and as you cool it at low temperatures, they'll align. This is, if you're living in 2 dimensions, this is known as one version of the XY model of magnetism. If you're in 3 dimensions, it's a kind of Heisenberg model, because I'm always writing down, in this particular case, something with as many components as there are directions in space. Here I've just said 2 components in 2 directions. You can imagine doing it with n components and d space directions in general as well. Okay, so that's the passive or equilibrium dynamics of a bunch of these vectors. Now let me use this same prescription. Say I'm going to say that this P variable is coupled to some chemistry, and therefore I'm going to augment this dynamics with a term proportional to the internal driving times this funny business that I told you about. I'll say that some off-diagonal coupling that couples P to the chemical variables, and that coupling can contain all terms allowed by the spatial symmetries of the system. So I should be able to make, each term here is a vector. dP over dt is a vector. Del F over del P is a vector. This noise is a vector. So I should write down the simplest vectors I can write down in terms of P, grad P, etc. What are those vectors? Well, there's P itself. There's, del squared P, Laplacian of P. What else is there? I claim that the simple kinds of terms I can have are either terms, okay, let me just say, look at this F, okay? If I differentiate F with respect to P, I'll get P dot P times P, and I'll get del squared P. These are the three types of terms that I'll get purely from differentiating F. So therefore, this term, this new term that I'm trying to introduce in terms of P has to be a vector. So it can be a term again of the sort that would come out of del F over del P, or it can be something completely new. So I'll take the point of view that if I get terms that are of the same sort as were already available from differentiating F with respect to P, I'll just lump them into a redefinition of the parameters in F. Okay, so it might shift the ordering temperature, it might shift the value of the average P at some temperature and so forth, but it won't introduce anything fundamentally new. The other thing it can do is introduce a term that could never arise from del F over del P, and that is this term. Okay. P dot grad P cannot be written as the variational derivative of any scalar functional with respect to P. Okay. The other thing that this guy can do is it can modify the noise, and it can modify the noise in complicated ways. I've started with the white noise. It can modify the noise by making the noise have some weird time correlations. I'm for the moment going to ignore that possibility. Okay, so what I'm going to say is that apart from terms that are already accounted for in P, and apart from annoying modifications to the noise, which I will not worry about, the term with the fewest P's and the fewest grads that I can create is this guy. And this guy could never emerge from this. Okay, so this turns out to be the shortest route to writing down a model, writing down what is known as the Toner-2 equation for flocks. It lacks some essential features. I've introduced only an orientation field. I haven't introduced any field that corresponds to the concentration, to the number density of particles in the system. I've assumed somehow that at each point of my system, there's an orientation, and I can forget about the number density. But this is already really interesting because this term says that rate of change of P, one of the contributions to rate of change of P is P dot grad P. What does that mean? What that means is that if I sit somewhere and then locally there's a little inhomogeneity in P, that is locally grad P is non-zero, and locally P on average is pointing this way, that inhomogeneity will get carried. So a local disturbance in this system will get carried by the local orientation in the direction in which it's pointing, much as a local excess density in traffic gets carried. Of course, in that case, it gets carried backward typically. Supposing you're moving in traffic and there's a little local excess, that pulse will tend to travel back through you. This kind of self-advection, self-carrying comes out purely from a general argument that says, if there's a coupling to some internal driving, terms of this form are allowed that weren't allowed in the equilibrium dynamics system. Okay, so that gives you an equation of those of you who have seen the equations of fluid mechanics will recognize that this is exactly the way in which the velocity field in a fluid advects itself. All of a sudden, you've gone from having an ordinary derivative to having something that looks like a material derivative. You can go further. You can divide through by lambda. You can rescale time to 1, and P becomes, you can rescale time by lambda, and P behaves exactly like the velocity field of a fluid. So this is a very funny, this model is a very funny chimera of a minimal model for the ordering of a magnet and a minimal model for the description of a fluid. The reason it's not just a fluid or just a magnet, it's obvious not just a magnet because the spins in a magnet don't transport themselves. They don't even directionally send information about themselves. They interact with everybody in all directions in the same way. But it's also not an ordinary fluid, because if you think of P as a velocity, then this term, when it's negative, says that locally, all of a sudden, a state of non-zero velocity with respect to some substrate is favored over a state of zero velocity. That means that if you thought of P as a velocity or a momentum, this normally you would have a positive damping. You would have minus some damping times P, right? Here you have a coefficient which can become negative. You can have a negative damping. And negative damping means it's a pump system in some way. So if you interpret P as a velocity, then P dot grad P is a totally natural thing to have. But then the idea of spontaneously acquiring a non-zero velocity out of zero is not something that happens in an equilibrium system. So if P is a velocity, then negative damping is unnatural, is disequilibrium. If P is an orientation or a magnetization, then P dot grad P is weird. So you can view it as a marriage of two seemingly very different effects, okay? And that gives you this equation. There's another very interesting way in which you can obtain this term, and that pertains to, just a second, let me, let me tell you, before I go further, let me tell you slightly more generally how one builds equations of motion for these kinds of systems. Supposing somebody just gave you this system and said, you know, in my laboratory experiments, I see that at high temperatures or at high noise, things are pointing at random. At low temperatures, spontaneously, they break a continuous invariance under rotation and pick out one direction. Can you please tell me how to write down the long wavelength, long time dynamics of the system? I'll say that if it's a bunch of little rotors, and let's say there are a bunch of rotors interacting with each other, but actually not suffering any friction with respect to a substrate, then the spin angular momentum of these rotors is conserved. And therefore, okay, let me make a general statement. The variables you need to describe this slow, large-scale part of the dynamics of a macroscopic system are the local densities of conserved quantities, the variables that correspond to a broken continuous invariance, and if you are at the threshold of a continuous transition, the variable that is going critical, the variable that is undergoing a continuous onset. Conserved, broken symmetry, and critical. These are the three kinds of variables you need. For all of these variables share one important property, which is that their characteristic time scale goes to infinity as the length scale involved goes to infinity. In the case of conserved variables, because basically if you've got a variable governed by a conservation law, then an inhomogeneity on a large scale can relax only by disturbances reaching the boundary of the disturbed region. The larger that disturbed region, i.e. the longer the wavelength of the disturbance, the longer it takes that variable to relax. If I have a variable like the angle of a continuous spin, a spin in a continuous spin magnet, if you rotate all the spins by the same amount, then they don't know they've been rotated. Therefore, if you rotate spins in a long wavelength way, let's say all these guys like this, all these guys like that, all these guys like this, then that variable takes a long time to relax because it's almost a uniform rotation. The characteristic time scale again goes to infinity as the wavelength goes to infinity. And at the critical point, you know that the linear order restoring force for a uniform disturbance goes to 0 at a second order phase transition. So that's the other kind of variable. In the present problem, when the variables concerned are for this particular problem, if you actually have spins on a lattice, spins with a conserved angular momentum, then the angular momentum density is a slow variable. The energy density is a slow variable. The order parameter magnitude, the vector order parameter describing orientation becomes slow at the transition. And angular fluctuations of the order parameter are slow in the entire low temperature phase. So if you want to describe a lattice, an array of rotors interacting with each other, then the full set of variables you need are all of these guys. Okay, you can read about this rotor lattice in Chaikin and Lubensky, chapter 8, for example. Okay, now supposing you take the same system and make it active, you give it a sustained energy throughput. Okay, so now you don't have to worry about energy conservation. I said energy density was important. Now you're pumping the system with energy, it's consuming energy and throwing energy out. So now I've got rid of the energy density variable. Okay. Secondly, I no longer have Hamiltonian to the system because I'm driving the system. Okay. So it's merely because I have rotation invariance, I can't guarantee that angular momentum is conserved. Because now I'm placing the system in contact with an ambient medium. So for my rotor lattice, only the order parameter magnitude and the angle are conserved. So let me try to write down a dynamics of a system of this sort. Okay, let me write down starting with the orientation and the conjugate angular momentum. Then this is the kinematic. If I was just writing down Hamiltonian dynamics, the kinematics of the orientation would be that P dot is S cross P divided by some moment of inertia. If I didn't have damping, S dot would just be the torque, and the torque would be P cross a local aligning field given by the neighboring spins, neighboring rotors. Okay. If now I say that these rotors are pointing in space and I'm not at equilibrium, so I can insist that I think I have a cartoon somewhere. Imagine I've got two rotors pointing like this and like this. This rotor is pointing towards this rotor is pointing away from this rotor. Imagine this rotor had eyes in its head, so it could see this guy very well. And imagine this guy had eyes, so it could only see sort of out of the corner of its eye badly. Then it might turn out that this guy's response to this guy is different from this guy's response to this guy. So what will happen is this one would turn less and this one would turn more in the process of alignment. That would mean, in other words, that this guy would feel an interaction coupling that is, I'll call it J plus A, and this guy would feel an interaction coupling that's J minus A. Okay. So then I write down this interaction that produces the aligning torque between spin I and spin, between rotor I and rotor J in this form, where I'd say that Jij is J plus something involving the angle between the way the guy is pointing and the vector connecting the ith guy's position to the jth guy's position. Okay. you did this, if you allowed this non-reciprocal interaction, because the system is now in a driven state and it is under no obligation to be described by an energy function, then you get a very interesting dynamics, which has this funny form that, as I said, this guy can respond more to that guy than that guy to this guy. And if you take this set of equations and adopt a smooth description, go to a continuum limit, then you will find that the torque, the local torque density is P cross P dot grad P. If you allow the angular momentum to relax, so we eliminate the angular momentum S in favor of P, you get a description in which P dot aligns on average with the surrounding P's through an isotropic coupling and has in addition a term P dot grad P. So purely allowing the interactions to be non-reciprocal, there is a spin back, a vector, a rotor back here to interact with the rotor in front of it, with the rotor towards which it's pointing, differently from how it interacts with the rotor away from which it's not pointing towards. You end up getting this curious phenomenon of self-advection. So you get the toner to flocking model purely from the fact that you allow a non-reciprocality of interactions. Okay, so basically, you know that if you have objects interacting with each other in real life, someone can be attracted to someone else, whereas that person can be repelled from this person. You can have systems in which you can have pursuit and capture in things like predator-prey models. You have an object that's pursuing something, another object fleeing from something. All of those interactions that can't be drawn from a potential energy of interaction. And here what I'm arguing is, even if you wrote down the simplest model for a set of rotors on a lattice, if you allow an interaction in which a rotor affects the rotor towards which it's pointing differently from how it is affected by that rotor, you immediately get this self-advecting property of the orientation variable. Okay. So this is interesting because it says that in order to get behavior for the variable P, for the orientation variable P, to behave like a velocity, it doesn't even have to travel. Only information about its orientation has to travel. Okay. So what I've done is in two different ways I've motivated flocking models. One, by arguing that in general, this principle of saying that if I'm out of equilibrium, new terms can arise in this way. Secondly, by saying that non-reciprocality gives rise to these kinds of terms. Third, I'm going to tell you, if you wrote down flocking models by saying that you've got particles that want to align with each other, let us say you've got a bunch of little arrowheads like this, and you make a rule that they want to line up with their neighbors in a certain neighborhood. And also, if you like, you can put in some cohesion and some collision avoidance, but those are actually not so crucial in this. If you just start with a model of particles in the continuum, and each one wants to line up with the average direction of its neighbors in a neighborhood of fixed size, and then it moves in the direction which it's pointing, that model also, if you co-screen it up, again turns into the toner 2 model, but then it has one additional feature. Because the particles are actually moving, you can count the local number of particles, you can talk about their local number density, and the current of those particles, that is the number flux, the number density to the velocity, is proportional to the concentration times the local orientation. And so from this model, from the Vichek model, which of course is not invented by Vichek, but by Reynolds and so forth, you get the toner 2 equation for a concentration field and an orientation or velocity field. Okay. So that might be a good place to stop. I've just reached where I wanted to reach for the first lecture. So maybe we can have questions for a few minutes, if you have any questions.
Yeah, I have a question. Can you just mention a word on how to make the link between the Vichek model and the continuum? How can one coarse grain?
Okay, I'll spend a few minutes on this. So I haven't got slides on that here. What you do is you define a concentration field. That is, you take the particle level description, and just like when you do fluid dynamics, you describe the local number density by saying, at the location of each particle, there's a delta function of concentration. And then I smooth that and say, in a little neighborhood, the local number of particles divided by the area of that neighborhood is the concentration field. And the local average of the orientations. If I assign a unit vector to each one of these guys, I don't think I have slides on that. If I assign a unit vector to each one of these guys and add them up and divide by the number, I won't get a unit vector anymore. I'll get a local vector, right? If I add up n unit vectors and divide by n, that object will be not a unit vector, but a vector with some magnitude and some direction. The direction will be the average direction of all these guys, and the magnitude will be less than 1 because not all of them are pointing the same way. That will become the P field. And the concentration, the number divided by the area will become the concentration field. And you can either write down an evolution, because you have definitions of those microscopic variables, definitions of the coarse-grained variables in terms of the microscopic variables, and an explicit dynamics of the microscopic variables, either in terms of an update rule or a collision rule. You can either do treatments that are like the Boltzmann equation or like a Fokker-Planck approach to get these kinds of equations from that. If you like, in the next lecture, I can talk about that. I was going to talk about Boltzmann fluid. And you can, so there is work by Bertin, BERTIN and company around 2006 that explicitly derives the flocking equations from these particle equations.
Okay, thank you.
Essentially an extended Boltzmann equation, the way you derive fluid dynamics from kinetic theory.
And a follow-up, a question on the treatment of how one would reach these out of equilibrium equations. So one can start with, let's say, Ginzburg-Landau type equations with the free energy functional.
Right.
And that gives you your equilibrium terms. And then you can start assuming the addition of terms that are not allowed by, the symmetries.
That are allowed by the spatial symmetry, but would not
come from the energy functional.
Yeah, right.
And my question is now with the big amount of data that we have, can one start making use of data to infer parameters with all sorts of expansions?
Yes, actually, that's a very good point, and that actually reflects some current trends in the field. I have not worked on that, but I know that I've certainly seen work on that recently, where you take, let us say, an active pneumatic that has gone into a turbulent state. I'll tell you in the next lecture about active turbulence a little bit. You observe the dynamics of a system of elongated objects that is active, and you can apply machine learning methods to try to infer the best values of the coefficients. So that kind of thing. Typically, you have data and you have a reduced set of equations onto which you want to project that data. And then by various kinds of least biased ways, you can try to predict those out. There's many, as in all these things, there are many ways of doing it. It's a bit of an art. But yes, there are indeed ways of doing that.
Thank you.
Adding on that question, I would ask you that if we are trying to do that, to fit this equation from data, do you think that normally when we're treating a model, let's say that you have data on some kind of behavior of some active pneumatics or active particles, would you then try to fit it to an already known model like VICSAC, or try to impose the model on it, or do you think that?
I think the point is that it's probably wisest to start to try to project onto the simplest possible model. And then if you find that numerically or analytically solving that model doesn't give you the phenomena that you see in the experiment, then you know something is wrong. There's something is missing at least. So
then after obtaining your equations, you would see phenomenologically if the solution resembles your original system, and that's how you judge the...
Yeah, because typically you're unlikely to get two equally good candidates for a given set of phenomena. But I must confess, I'm not a practitioner of that whole approach of projecting out best, maximum entropy or least bias or machine learning ways of doing things. So I don't have a direct experience with it, but I would guess, as with any type of theorizing, you first make the simplest possible assumption, try to see if that works, and then modify as and when necessary. So that would be the way to do it. The reason that's important is that because in any of these models in which you have, let us say, a local density field, every one of the coefficients in the model can depend on that density. So in a sense, the possible set of PDEs you can write down to describe these systems is unboundedly complicated. And you will just get completely lost, particularly because this annoying property of density dependence. And that's actually a problem for analytical theory also. Toner and Tu neglected certain concentration dependencies in their original formulation and made predictions which we now know not to be quite right, although we don't know what the right answer is.
Right. Yeah, because the risky thing is that if, for example, different models, even if they miss on the actual nature of the system, for example, you can have the reactive matter, but try to model it in a different way and get phenomenologically good results that don't really resemble, don't match the actual description of your original system in terms of conservation laws or stuff like that. So probably this is why it would be risky.
I think one thing that's important is to build the conservation laws. If you know that you're in a number conserving system, then you absolutely build the conservation law even into the trial equations of motion that you're writing down. Right? You don't want to lose those. So conservation laws and spatial symmetries you build in. So you don't expand your search space to leave the sector where there is conservation and whatever symmetries you know your system to have.
Right.
Right.
Thank you.
Okay.
I think there are no more questions.
Yeah, fine. And I'll go get my dinner.
Okay. Until the next time, which is going to be Thursday, same time, and looking forward for the upcoming talks. Thank you.
Thanks a lot. Bye.
Bye.